So this is ELC111, and we'll finish up our discussion of analog to digital converters by talking about the sampling rate of A to D converters. Now, the sampling rate is merely the rate at which we obtain a new digital value, or the rate at which we acquire a new digital value. And I provide the block diagram of an A to D converter and its connections to the microprocessor. And again, we looked at this block diagram in the previous presentation. So our A to D converter has an input voltage and a reference voltage and some digital output. And again, remember the resolution, the smallest change in the input voltage that can be recognized, is determined by the reference voltage and the number of bits in the digital output. And the digital output is sent to a microprocessor or a microcontroller. This is the brains of the whole operation. And the microprocessor has to send a signal to the analog to digital converter in order for this block, this component, or this circuit to make a conversion from analog to digital. And of course, the A to D converter sends an end of conversion signal back to the microprocessor to let it know when it's finished. And the microprocessor, of course, outputs information to memory and or to a display unit so that we can capture and hold this digital information and of course display it on something like an LCD display. Now, one of the terms that you need to be familiar with regard to the sampling rate is what's called the Nyquist Criteria. And we can also talk about this as the Nyquist Frequency. And what the Nyquist criteria states is that the minimum sampling frequency has to be 2 times the input frequency. That's Quency. So the Nyquist criteria simply states that the minimum sampling frequency has to be 2 times the frequency of the input signal. Therefore, the Nyquist frequency is 2 times the frequency of the input signal. Now, most EEG systems have a 240 hertz sampling rate. And this by far satisfies the Nyquist criteria for EEG signals. The EEG signals, the delta signal is less than or equal to 4 hertz. The theta signal ranges anywhere from 4 hertz to 8 hertz. The alpha signals range anywhere from 13 hertz to 30 hertz. And the beta, oh, I'm sorry, I got that wrong. The alpha signals are anywhere from 8 hertz to 13 hertz. The beta signals are anywhere from 13 hertz to 30 hertz. And the gamma signals are anywhere from 30 hertz up to 80 hertz. Now, when we remember that we're one of the problematic noise issues in EEG measurements is the 60 hertz interference that we get, or 60 hertz energy we get in our system. So the 60 hertz information is really going to be filtered out by our low pass or high band pass filters. So generally speaking, the gamma information is going to be limited to anywhere from 30 hertz to 60 hertz. But regardless, with a 400 hertz, 240 hertz sampling rate, we more than meet or exceed the Nyquist criteria for all these frequency signals. Now, another term that you need to be familiar with regards to sampling rate is what's called aliasing. And aliasing is simply what happens when we sample a signal too slowly and we observe a different signal. Yeah, different, fit that in right here, a different signal. And again, aliasing, if we look up the definition, aliasing is that what happens when we cannot discern or differentiate between the input signal and some other signal. So I've sketched out an example of a sine wave, and this sine wave is all above 0 volts. And it was easier for me to sketch in a sine wave than it was to sign in a delta wave or a theta wave or any of the other waveforms that you would observe. But this still works for our definition. And then I've sketched in here the start conversion signals that is sent from the microprocessor to the A to D conversion. And if we look at this start conversion pulses, we can see that these start conversion pulses do not meet the Nyquist criteria because we're not sampling twice during every period of the waveform. One period or one cycle of the input waveform is from here to here. So that's one cycle. And again, to meet the Nyquist criteria, I would have to sample this signal twice through one cycle. So what's going to happen, again, the analog to digital converter will look at VN and convert that analog voltage to a digital value right here and right here and right about here and right about here and then right about here. And it's going to send this digital information to memory and then send it to the display unit to reproduce this captured information as a waveform on the screen. So we're going to send information here. We're going to send information here. We're going to send some information that's about right in here somewhere. And then somewhere down here, that's about 1.5 divisions up. And then some division, or excuse me, send some information right down here. So when this digital information is sent back to the screen, what we would see on the screen is a waveform that looks kind of like this. There we go. That's not, well, that's not that good, but it's all right. So what we would see on the screen is a waveform that has a much lower frequency, a much longer cycle time than the input waveform. And this happens solely because of the fact that our sampling rate is much too low for the frequency of the input signal. So in order to recreate this information on the screen, we would have to sample it at least here and 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 here. We would have to sample it at least twice for every cycle of the input waveform. Again, from this point to this point is one cycle. So then we could actually reproduce this information on the screen. We would have, see, that's up here, and then that's down here, and then that's up here. Oop, I lost the first one's up here, sorry. Right here, down here, up here, down here, up here, down here, up here, and down here. So now the information we would see displayed would replicate or show us an approximate value of, ooh, paper slipped, of the input waveform. So we have to sample this signal often enough to be able to recreate the input waveform. Now, again, the Nyquist criteria gives me the minimum frequency. Don't confuse that with the optimal frequency, because to truly recreate this waveform in a digital fashion, we would have to sample it much more often than twice every cycle. We would have to sample it here and 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 here in order to more accurately display or capture that analog information. So again, the Nyquist criteria is solely the minimum requirements.